Alright, silly people, here's the situation. This time we're going to be writing the QR algorithm, which, first of all, it's going to decompose the given matrix A into a orthogonal matrix Q times a upper triangular matrix R. Um, and that is a really useful thing for solving for eigenvectors and eigenvalues. So that's kind of the motivation behind it. So the Q and R matrices will look like this. So the Q columns the Q vectors form the column of the Q matrix, and then R follows this sort of pattern here, where the Q vectors are defined up here. So the first part of the problem is actually to prove via induction that the columns of the Q matrix are orthonormal, and I did that down here via induction again. So the idea is you have to start with the base case. So there are two different base cases for this proof. One where I is equal to j and they're both equal to 0. Pretty easy to prove that q dot q in that case is equal to 1 if you just expand the definitions of q's and then also expand the definitions of the u's that comes from. And then also the other base case where I is not equal to j, but I equals 0, then you can just choose whatever j value you want. I just went with 1. And also prove that that is equal to 0 just by, again, expanding q and also u whenever it came up. So that is also equal to 0. So then you can assume that for all integers less than k and l, less than or equal to k and l, that it's orthonormal. And more specifically, you can ascribe a value to that to be 1 specifically, so that when you plug in l plus 1 instead of l, you can show that you get 0 eventually. The crux of the proof is that whenever you get to the part where you expanded q sub l plus 1 into its summation form, you end up with this inner product of q sub k with q sub j. Since j is, by definition, in the summation formula, less than l plus 1, and it's also less than l, you can definitely use the Kronecker delta formation of that. So it'll be the Kronecker delta delta jk, which means you can kill off the sum that it's in, and now you just have two of the same inner products. One is positive, one is negative, so they cancel out and it's 0, right? So it's a pretty nice little proof. Do it yourself. It will help you understand this problem, I think. But now we can get into the actual part where we're solving the code, right? So what I have here is just basically the input array that we want to test our function on, but we have to write the function. So I'm going to call it QR. It's going to have to take the arguments a square matrix. Eventually it's going to return q and r, but we have to calculate what those are, right? So first you have to figure out how big the square matrix is. So I'm going to call that n, and it can be calculated by getting the length of the first row or the first column of the square matrix. It doesn't really matter. You can define it like that. Now you can set up the matrices. Q, I'm going to make an empty matrix because it doesn't really matter what initial values it has. I'm going to have to update all of them. And n by n1 with float values. And also R, which I'm going to start out as a zeros matrix of size n comma n, also with float values. Okay, we can go ahead and fill in what the first column of the Q matrix is and the first element of the R matrix is. Since we know that the first column of Q is Q sub naught, which is U naught over U, or U naught over norm U naught, which is A naught over norm A naught. A naught being the first column of the A matrix. So I'm going to go ahead and just hard code that in. Q the first column, so colon comma 0, is equal to a colon comma 0 divided by the norm of a colon comma 0. The first diagonal element of R, so R is 0, 0, will also just be the norm of the first column of the A matrix. So colon comma 0 here, dot norm. Okay. The rest of the values of Q we will fill in a loop. So for I in range, just go to n, and we can start at 1 actually. We don't need all of them. We will first of all calculate a U, which is going to be given by this formula here, U sub I equals A sub I minus a sum. So we'll have it first of all equal to just A indexed colon comma I, so whatever column of the Q vector we're working on, and then create a sum over J for J in range. This sum goes from 0 to I minus 1, so we can just have it run from 0 to I, right? Python stuff. But yeah, in here you just subtract off from U the dot product between, it's the dot product between Q sub J and A sub I times the vector Q sub J. Okay, so we'll do the np dot Q indexed colon comma J comma A indexed colon comma I, and then multiply that by Q indexed colon comma J. That's equivalent the way that we've set it up. When we figured out what U is, we can put it into the matrix. So now Q colon comma I can be said to be equal to U divided by the norm of U, and also R, the diagonal element anyway, so I comma I will just be given by the norm of U. And I just remembered, make a clever distinction. If you just set U equal to A, then when you go through this process, you're also going to be changing A as you go. You don't want to do that, you just want to change U. So what you do is you make it that row dot copy. So it's identical to the whatever column of A that you're working on, but you won't be changing A as you go to make it work. Okay, so that loop takes care of every column of the Q matrix and the diagonal elements of the R matrix. We just need to fill in the off-diagonal bits of the R matrix to finish it out. So let's do for I in range n, so to get every row that's left, and also for j in range I plus 1 to n, so the off-diagonal elements above the diagonal. That Rij, it's equal to Q indexed by the row dot A indexed by the column for every off-diagonal element. So okay, we'll do the numpy dot Q indexed by the row, so colon comma 0, and then comma A indexed by the column. It's not 0 here, it's I, but then this is colon comma J, right? Is that easy? Yeah, it's that easy. Okay, cool. With all of that, the code should return the proper values of Q and R, and we can check this by running it. So Q, we can say that Q comma R is equal to QR of A, and you can print the dot product of Q with R And if we did the code right, it will return a matrix which is identical to the one that we put in. So let's give it a go. And it looks like it worked. So this function is good. But now we also need to figure out what the eigenvalues of A are using our little function. So the way to do that is you want to set up a new matrix called V, which is what we're going to store the eigenvectors in. So you start it off as the identity matrix of size n, better figuring out what n is outside of the function. So n is going to be the length of A indexed colon comma 0 comma 0. That should do it. And you also want it to be float values, obviously. You're going to set up an accuracy that you want. Newman suggests we use 1e to the minus 6, so 10 to the minus 6 accurate. An initial error value, which I'm going to make arbitrarily large. I'm just going to make it Avogadro's number. And then do a while loop while error is greater than the accuracy. We can check what the errors are first. So we'll create a couple lists. Eig_ls equals empty list. That's going to store the eigenvalues as we go in. And then off_ls being the off-diagonal elements. This is to help us calculate the error, since the error is going to be the maximum of all of the numbers that are off-diagonal elements in A, right? So for I in range n, for j in range n, we're going to append the eigenvalue list with the diagonal elements. So if I equals j, then you do this, append A indexed I comma j. Otherwise, you can append the value of A that you're on to the off-diagonal list. Right at the end of that loop, you can see that and actually, all we want is the absolute value of this number, actually, because all we're using is to get an error. That error will be equal to the maximum of the off-diagonal list. Okay, so that's cool. If it finds that the error is still greater than the accuracy, then the code will keep going. So what you want to do at this point is you want to, first of all, multiply v by q. Well, we need to calculate q first, I guess. So q comma r is equal to qr of a. Multiply v by q, so you say v is equal to v dot v comma q, and then update a to be a new thing, which is going to be the dot of r with q. And then when it finishes running, we can have it print out the eigenvalues, which is going to be eig_ls, and also print out the eigenvectors v. All right. So let's give this a go, see if it correctly, okay. So I think it got the right eigenvalues, it just doesn't look very pretty. I'm just going to do for eig in eig_ls, print the float version of eig. Okay, yeah. And so the problem statement does say that the eigenvalues of this are 1, 21, minus 3, and minus 8. So you can see that we got 1, 21, minus 3, minus 8 to pretty high accuracy.